All right, let's go through this. This is using what we did yesterday. So we're trying to graph log base 2 of x. I did not tell you what our exponential parent function was, but what is our exponential parent function? 2 to the x. So we're going to start by looking at the table for 2 to the x. Where we wanted that good view of the middle, our -2, -1, 0, 1, and 2. Whoever's listening to something in this general corner, turn it down. If you don't care about your grade, you don't get to tank everyone else around you. That's what it tells me when you're staring at your phones or watching your headphones or watching your phone while I'm talking, is that you don't care about your grades. And if you don't care, why do I care? Just saying, about half of y'all ain't paying attention to me. So, let's get off my back. You just get to take the class again. Because this class is required for graduation. Just saying. All right. So, when we're filling in our y values, we have our 1/4, our 1/2, our 1, 2, and 4. And we know that exponentials have an asymptote at y equals 0 for that parent function. For our logarithm, what we need to do to get log base 2 of x is we're going to take that 2 to the x and we are going to make everything swap sides. So if it used to be an x, it's now going to become a y. And if it used to be a y, it's now going to be an x. Bless you. So everything in the y column goes to my x column. So we're going to have our 1/4, 1/2, 1, 2, and 4. And if it used to be in the x column, it now goes in the y column. So we're going to have our -2, -1, 0, 1, and 2. And instead of having a y equals asymptote, we're going to have an x equals asymptote. Oop. So when we go to graph it, I'm going to graph that asymptote at x equals 0. That is a vertical line like this. And then when we plot up our points, we have our 1/4 -2, 1/2 -1, 1, 0, 2, 1, 4, 2. Yes, dear. Yes. Okay, so that's where we stop on this. Today we're going to start working in our transformations, which are going to be the same way we did transformations for kind of everything else we've done for forever, with A, H, and K. So I put this page up here at the end of yesterday so we could write stuff down. I'm going to talk us through some things on here. Looking at transformations for logs. This is our transformation form. We still have our A value out in front. We still have the H inside and with the opposite sign. We still have K added on the end. Just like with exponentials, that b just decides our parent function. So log base b decides our exponential parent function. It doesn't do anything for transformations. And because we always had a horizontal asymptote of y equals k in exponentials, because it is the inverse of exponentials, we're going to wind up with a vertical asymptote of x equals h. So just like it was always y equals k, this is always going to be y equals h. Logarithmic functions have a domain. They're going to be, it's very similar to how when we had exponentials, it was k to infinity. This is going to be h to infinity. And a range of all real numbers. So negative infinity to positive infinity. So exponentials, we used k a bunch of times. In logarithms, we're using h a bunch of times. So it changes our domain and it tells us where the asymptote is. We're going to set these up exactly the same way we have done everything else for A, H, and K. They have the exact same jobs. A still tells us if it's a stretch or a compress. H is still our horizontal shift. K is still our vertical shift, like a kite. It goes up and down. All right. So here's our first one. We are going to graph the parent function as well. So I want to graph the parent of log base 3. Which means we are going to wind up making 3 tables for these. Because I'm going to start with the parent of the parent, which is our exponential that has the same base. So we're going to start by making the table for 3 to the x. That's a y. And I know it's very small. This is where we have our -2, -1, 0, 1, and 2. For our y values, we have to evaluate it. I'm going to make my pen a little skinnier. And we get 3 to the power of -2, which is 1 over 9. 3 to the power of -1 is 1 over 3. 3 to the 0 power is 1. 3 to the first is 3. And 3 squared is 9. So we're not going to graph that part, but we are going to come over and graph log base 3 of x. This is what we're calling the parent function of the logarithm, which is the inverse of this exponential. That's about to erase it. That was not what I wanted. There we go. Of this exponential. So what was the y becomes the x. So my x's are 1/9, 1/3, 1, 3, and 9. And my y's are the -2, -1, 0, 1, and 2. If you can fill this table in without doing the exponential, that is totally fine. But it's not always easy to do that. So I'm going to graph that one up on the graph. My 1/9 -2. My 1/3 -1. 1, 0, 3, 1, and 9, 2. Yes, sir. Oh, yeah, sorry. I have a whole bunch of... Wow, yeah. That'll make it way easier if I actually pass out the graphs. Oh, I forgot to put milk in my coffee this morning and just throw me off. Muffle day. I have to go find the teacher's office so I don't have to clean the fridge. Yes, I already passed it up on my desk. 100% space given to that one. I need to grab the bin to bring it over next to me. And I'm gonna grab the food dishes. That one literally fell out. Sorry, y'all. I need to drink way more coffee to get myself functioning. So hot, I forgot to put milk in. So hot. Okay. So I'm gonna give you guys a second to get this graph down there before we go into identifying our transformations. Our first thing we're gonna need to do is to figure out what is our A, H, and K. So I'm going to write our transformation form up at the top so that we can look at it and use it to help find pieces. So we have A, bless you, log base B of x minus h plus k. Let's see, where were we? Oh, right over here. All right, so the first things we're going to do before we go on to the next step is we're going to figure out what are A, H, and K. So what do we notice? What do we see? We don't have an A. There's nothing multiplied out in front. If there's nothing multiplied out in front, our A is actually 1 because it's multiplied, not added. So there's an invisible 1 in front of it, which just means there's not any transformations. There is no stretch, there is no compress, there's no reflection over anything. It just is. How about H? H is inside and has the opposite sign. So what is our H? -4. Yes. Which means which direction does it move? Left. This has gone left 4 units. How about our K? -5. What does that, which way does that move it? Down. So we're going to take this whole logarithmic function, pick it up, and move it left 4, down 5. So the way we're going to do that is we're going to come up here and we're going to take our table, our logarithmic table, and we're going to do transformations the exact same way. We're going to do our x plus h and our y times a plus k. So in this particular case, we're going to do x minus 4 from our parent table. Grab my kind of blue X. We're going to take our y's times 1 minus 5. So just like we've done for all the others, we're going to take these x's and subtract 4. We're going to take these y's and subtract 5. And we're going to need to be really careful. These ones have fractions in them, but we're just subtracting right now. So we might be able to do it by hand. We might want to type it in the calculator. Either way is fine. So if we have 1/9 minus 4, we're going to have negative 3, bless you, and 8/9. Or if you put it in the calculator, it's probably say negative 3.88888888888888.
So can we put the negative 3.8888?
Yeah, that's fine. Totally fine. The only time I ever actually look at your tables is if the graph is off, and I'm going, what the heck happened? Okay, so the tables are a tool for you to use to make sure that our graph is right. But I always start with looking at your graph. And if your graph is good, I just barely glance over the tables. The tables are for you to do the thing. I took the 1/9. This one. 1/9 minus 4. So it's going to be this one. Now we're going to do this one. So we're going to take our 1/3 minus 4. It's going to give us negative 3 and 2/3. Or it'll probably give you 0.666666666666. And that's also fine, again. I don't care if you do fractions or decimals. I just really don't recommend mixed number or improper fractions because, let's see, negative 11/3 would not be easy to graph off the top of my head. So then we get into the whole numbers and they're way easier. We have 1 minus 4, which is negative 3. 3 minus 4, which is negative 1. And 9 minus 4, which is 5. So we take each of these x values and subtract our 4. We're going to do the same thing with the y's. We're going to take each of these y's and subtract the 5, because the times 1 doesn't do anything. So negative 2 minus 5 is negative 7. Negative 1 minus 5 is negative 6. 0 minus 5 is negative 5. 1 minus 5 is negative 4. And 2 minus 5 is negative 3. Then I'm going to pop all the way down to the bottom of my page here, and I'm going to write down our asymptote. Our asymptote is going to happen whenever we have x equals h. So our asymptote is going to happen at x equals negative 4. It also gets shifted left. So the asymptote still moves with those transformation. My x plus h, I need to add that h into my parent table asymptote. So my asymptote is not going to be over here anymore. It's going to be way over here. So that's the next piece I'm going to draw. So my asymptote for a transformed function is way over here at negative 4. It's always going to be x equals h. It's always going to be x equals h. And since our h was negative 4, it's x equals negative 4. So then let's plot up each of those individual points.
So that one you always draw like a dotted line.
It's not like law, but it's a common practice. Most people do asymptotes as dotted lines. But it's just, I think, because it's been habit for years and years and years. So it's not like a law, it has to be a dotted line. It's just one of those things that everybody does and no one knows why. All right, so let's plot up our points. We've got -3 and 8/9, and -7, which is really close to my asymptote, and way down here. -3 and 2/3, and -6. So still pretty dang close to my asymptote and way down here. -3, -5. Yay, we love whole numbers. They intersect so much easier. -1, -4, and 5 way over here, -3. So our transformed function looks like this. What we did was we took this blue logarithm and we moved it left 4 and down 5, and we wound up right over here. So that's all this is it took this blue guy left 4, down 5. Our last piece of this one is to get our domain and range of the green one, of the transformed one. So what is the domain of this green one? -4 to infinity. Our domain will always involve our h in some way, shape, or form. In fact, it's almost always going to be h to infinity because we're not doing y reflections as far as I'm aware. How about our range? All real numbers. Or for -infinity to positive infinity. The range is always going to be all real numbers. So there's a lot of pieces on here, but aside from the logarithmic table being new yesterday, nothing's new today. Like, it's all the same stuff. So let's do another one. More new pieces. So we're going to do, our goal is to get this guy graphed. We're going to start with graphing our log. So we're going to graph our parent log, so log base 2 of x, which means the first thing I need to have is my exponential table. Which I'm going to do in kind of gray. So our exponential has what base? 2. So 2 to the x is where I'm going to start tables-wise. We use our x's from -2 to +2. And we calculate our y's into 2 to the x. So 2 to the power of -2 is 1 over 2 squared, or 1 over 4. 2 to the power of -1, that's 1 over 2 to the first, or 1 over 2. Anything raised to a 0 power is 1. 2 to the first is 2, and 2 squared is 4. Easter. Yeah, let me write your pass. So then let's do our log table. This one we are going to graph. So we're going to do log base 2 of x, where we're taking our x's and our y's from our exponential table and switching their spots. So I'm going to go write a pass. You guys start switching them, and if you get all the way switched, graph it. All right, so we're going to wind up with x's that are 1/4, 1/2, 1, 2, and 4, and y's that are -2, -1, 0, 1, and 2. And when we graph that, we're going to have yeah, there we go. So we should have a graph that looks like this. So that's our 2 to the x. That's exactly what we did as the bell work today, too. So then we're going to need to do our transformations. And we're going to do our x plus h and our y times a plus k. That means we need to know our transformation form. And we need to know what our a, h, and k are. Base b, x minus h plus k. So let's identify our pieces first. What is our a? 2. Which means what transformation is happening here? Is that a stretch or a compress? Stretch, because it's bigger than 1. Does big kid yoga. It goes big, tall, and stretch. What is our h? +3. So this is going to move which direction? Right. How about our k? 4. So it's going to move which way? Up. Goes up 4. So when we're doing our transformation table, we're going to take all of our x's from our parent, and we're going to add 3. We're going to take all of our y's from our parent times 2 plus 4. So when we're filling in our table here, we're going to take our x's. So my 1/4 plus 3, well, that one's not too bad. That's 3 1/4, 3 1/4. 1/2 plus 3, well, that's 3 1/2. 1 plus 3 is going to give us a 4. 2 plus 3 gives us 5. And 4 plus 3 gives us 7. So we're doing the exact same operations we've done with A, H, and K for forever. So let's do our y's. I'm going to take my -2 times 2, which is -4. -4 plus 4 gives me 0. -1 times 2 is -2 plus 4 is +2. Zero times 2 is 2. No, sorry. 0 times 2 is 0. Plus 4 is +4. Bless you. 1 times 2 is 2. Plus 4 is 6. And 2 times 2 is 4. Plus 4 gives us 8. And we're going to have an asymptote at x equals h, or x equals 3 in this case. Doesn't matter what other transformations we have, it's going to be at your h value. So our asymptote for our transformed function happens way over here. It doesn't matter that it's going to go through my parent function. It's purple, not green. The green cannot cross the green wall. The purple can cross the green wall. It doesn't matter. It's not related. So when we plot up our points, we're going to have 3 1/4, 0, 3 1/2, 2, 4, 4, 5, 6, and 7, 8. And we can really see the difference this time in a stretch. You can really see that that's been pulled taller and skinnier. Like this has been stretched upwards. That A value of 2 has really taken this purple graph and grabbed on it, stretched it up. So our last piece on this one is to find our domain and our range. I am not talking to you. Oh my gosh. What even was that random trivia fact? She's so nosy. So nosy. All right. So we're looking at the green one up here. What is our domain? 3 to infinity. What is our range? All real numbers. I'm going to write it as negative infinity to positive infinity. It's really easy to see that on this one because it's so stretched. We really see that both of those arrows are pointing up and down. Okay. We're going to do one more, but it's got the same parent function. It's got the same base. So we're going to be able to use this same parent table to do our next one because it's going to be a log base 2. That way we save a little bit of time because I want to show us a reflection and what that does. So we don't have to go through to the 2 to the x all the way back to the beginning. We just made the log base 2 parent function on the last problem. Log base 2. Was this one. 0, 1, and 2. 1/4, 1/2, 1, 2, and 4. So it's the same parent table as the last time. That's what this log base 2 is. So we don't have to recalculate that this time. I wanted to save us a little bit of time so we could make sure to do this and not have to like squish. So I'm going to graph up my parent function real quick. It's the same parent function we did before. It's the same parent function we did in the bell work. One we've seen a bunch. One we will probably continue to see fairly frequently. Because it's very common and it keeps our numbers in like small, sane batches. P of x minus h plus k. So let's figure out our transformations. We want to know what's our a, h, and k. What do we see? A is -1. Which means this has a reflection. This is going to reflect across the x-axis. It's gonna go upside down. How about our h? +4, which goes which way? Right. How about our k? +1, so it's going to go up. So when we do our transformation table, and we do our x plus h, we're really taking the x's from our parent function, and we're going to add 4. When we do our y times a plus k, we're going to take our y from our parent function times -1 plus 1. So when we go down our x's, they're fairly familiar. We're going to have 4 plus 1/4, so that's 4 1/4. 1/2 plus 4, which is 4 1/2. 1 plus 4 is 5. 2 plus 4 is 6. 4 plus 4 is 8. The y's are where it gets a little bit harder because we're going to have our -2 times -1, which is +2. +2 plus 1 is +3. -1 times -1 is +1. Plus 1 is 2. 0 times -1 is 0. Plus 1 is 1. 1 times -1 is -1. Plus 1 is 0. 2 times -1 is -2. Plus 1 is -1. So as long as we go through it fairly carefully, we should be all right. We're still going to have our asymptote at x equals h, so x equals 4. So we're going to wind up with our asymptote over here at 4. And let's plot up these points and see what it looks like. This is our last bit. I don't think we're even going to get to domain and range because announcements are going to try and start. So we've got 4 1/4, 3. 4 1/2, 2. 5, 1. 6, 0, and 8, -1. So it made the whole thing flip upside down. It reflected across the x-axis. It made it flip over. It went upside down. Just like, Jesus, that scared me. Just like parabola, we went from happy face to frowny face. This went from L to okay. So the transformations aren't super different. We just got to be really, really careful with them. That is the end of what we wanted. We're just going to skip domain and range because the last piece you have on your homework are those 2 graphs, and I'm going to go turn on announcements. Oh, snap. We made it all the way to the end. Ha-ha! Victory.